yesterday I did record the notes, and then we just kind of stopped at this part right here. And then we have more notes to take today, which are just more examples. And so we're going to see if we can kind of squish all that in. But here's the big thing. If your equations are already set up with y in them, like x equals y something, or they're easier to write in terms of y, you can integrate with respect to y instead of integrating with respect to x, which is kind of what happened on the very first one I assigned you, that you just automatically took the y since it was x equals y squared and x equals y cubed. Most people didn't even think about it. You just automatically used y squared and y cubed. Luckily on that one, the bounds were the same on the x and the y axis, so it didn't matter. But what happens is you got the negative answer because you did it top minus bottom, which when you do on the y-axis, you don't do top minus bottom, all right? So it says, think about if you were doing Riemann sums here, right? They're talking about this lovely little rectangle here. When we do with respect to the x-axis, we draw our rectangles in like we always have. We haven't drawn rectangles in a long time because we're not actually using rectangles anymore, right? Like we actually do the integral. But remember, the definition of an integral comes from the fact that those number of rectangles go to infinity, so that's why they're drawing the rectangle in here. But look at these graphs. Do you agree that it would be hard to take the top function minus the bottom function in these graphs that are drawn like this? Right? Like which one's the top, which one's the bottom? So this is where integrating with respect to y is just easier, and it's very easy to do because you just take the functions subtracting themselves in terms of y, but really important that your bounds are on the y-axis now. So big things too that are different. So your bounds are on the y-axis. And the other big thing is that instead of doing the top function minus the bottom function, you're going to take the right function minus the left function. So notice on all of these, they say f of y minus g of y because they're taking f of y minus g of y, f of y minus g of y, f of y minus g of y. Or if I don't know if this makes any sense or not, but if you like top minus bottom, you could think about taking this graph and rotating it, right? Taking it and rotating it, and then it would be top minus bottom again. Let's see if I can really screw this up, right? If I took this and I rotated it, whoa. Right? If you rotate it 90 degrees, then the y-axis, looks like the x-axis, and then you do top minus bottom. I just do right minus left, but I used to say, because it was really hard, I didn't think about doing this, but we used to do this when we did this section. We would say, you just tilt your head sideways, and then you do top minus bottom, right? I don't know. I like right minus left, but however, it works for you. Something else that's easy to do, just like on number 3 that I made you do yesterday, if you check the back of the book and you got negative 1/12, but they have positive 1/12, then a pretty good clue is you subtracted in the wrong order. Right? So you did the opposite way of what you should have done. And so that lets you know that you probably did the calculus right, you just subtracted in the wrong order. Okay? So let's do one with y's. The hardest part is maybe figuring out which one's right and which one's left. Like this one. Maybe this is the only example we didn't do yesterday, right? So a big clue of when to use y bounds is when the equations are written in terms of y. Sometimes they're not written in terms of y, and then when you graph it, you can see that you should put them in terms of y. Do you know what this graph looks like? X equals y squared. Yeah, that's a sideways parabola, right? Because remember, y equals x squared is a parabola opening up. X equals y squared means it's a parabola opening to the side. If you don't know that, you can make an xy chart, but remember when it's solved like this, normally we pick our x's first. You have to pick your y's first and then go back and get your x's, right? But when you see y squared and x isn't, I hope you know that that's a sideways parabola. And the same transformations can occur, like when you move it left, right, up, or down. But you can pick some points here. Like if you pick 0 for y, you get 0 for x. If you pick 1 for y, you get 1 for x. If you pick negative 1 for y, you also get 1 for x. So this is not a function, right? It doesn't pass the vertical line test. And those are really the ones that it's useful to integrate in terms of y. Right, so we'll go like this. And then if I picked 2 for y, I would get 4, right? So this goes to 4, this goes to 2. Is that true? Like that? If it was negative y squared, it would open the other way. It's been a while since we've done conic sections, but. And then what about this? X equals y plus 2. How do you graph that? Well, you have 2 options. One option is we could just make an xy chart, pick y's, plug in the x's. It's going to be a straight line. The other thing is if you want to use slope-intercept form, you have to put it in slope-intercept form. You can't just say that the y-intercept of 2 and a slope of 1. Like, it doesn't work that way. So you can either make an xy chart, or you could flip it around pretty easily. Could we say this is the same as y equals x minus 2? Is that the same equation as this? And so if you want to use slope-intercept form on a linear line, you just have to put it in slope-intercept form. Yes? No? Or you could turn the page and then do it that way. So, but you can make an xy chart too and just pick points there. But it should have a y-intercept of negative 2 and a slope of 1. Graham Carr back in the day had this plan that when you graph on your calculator, right, like your calculator's y equals. So he says we can graph these on our calculator, but just change them to x's, and then you can turn your calculator sideways, and it would make it the correct way. I always struggle knowing which way to turn it, but feel free to kind of check that out, right? So like on your calculator, you could graph, you would type in x squared, and you would type in x plus 2, and then you rotate your calculator to see what it looks like. I don't know if that makes any sense, what I'm saying. There's a really cool app that you can't use on the AP test, but it's free graphing calculator app, and it actually has a version like where you can type in x equals instead of y equals, and so that's kind of a nice thing to visualize as you're doing these as well to see what's happening. Let me make my calculator fine. But anyway, we can look at it later. Here's what you're looking for. You're looking for that closed shape. What would my bounds be on here? Yeah, be really careful. I think the easiest thing to mix up when you're doing in terms of y is we're so used to taking our x bounds, but we have to take our y bounds here where this goes, which would be from negative 1 to 2. And then we just want to do right minus left, which would be, in terms of y plus 2 minus y squared. And remember, the setup is super important, right? There are some AP questions that the question is just set it up. Do not solve it. Because solving it is just the stuff we've been doing forever. It's you knowing how to set it up is the new part of this. And then it's just practicing our lovely integrals. The y-axis. Right? Where the shape is on the y-axis. Where it closes that shape. So let's see here. We would have to. Oh, that did not work, did it?
Rotate it left.
But then it's.
The line's backwards.
Yeah, I struggle.
The line would have to be negative x.
Yeah. I always struggle doing it.
So,
Yeah. I don't know. I'm just saying, I don't ever take credit for that idea because I don't. I struggle with it. I just graph it. Now we're just going to integrate it. So we're just going to say y squared over 2 plus 2y minus y cubed over 3 from negative 1 to 2. So that would be 2 plus 4 minus 8/3 minus 1/2 minus 2 plus 1/3. And again, when it says analytically, I want to see some work there. I want to see you integrating it. I want to see this step, and then if you want to use your calculator, you can use your calculator. But when I'm grading it, I want to see that you use the fundamental theorem of calculus by hand, and then we can go from there. But and again, I don't ever distribute that negative because I think it just causes more problems. But, oh, I got 9/2. Did you get 9/2? Yes, did anybody get this? Yes. It'll always be 9/2. We had 9/2 on the other example yesterday also. Questions about that?
Integrated using X or Y and your calculators or the same exact.
Yes, because it doesn't matter what variable you use, right? But what's important,
I mean,
you see what I'm saying? What's important is the setup. And the setup is where you have to think about it in terms of y and graphing it like that. Okay.
your boundaries still be the same. Still be maybe 1, 3, X. Even if you graph on both the X functions, your boundaries are still the same.
But do you do... I don't know. It does work on this one, but I don't know that it works on all of them like that, right? Like the one on the homework, the number 3 that I had you do, if you do it in terms of x's, you get a negative answer, right? Like you get negative 1/12 instead of positive 1/12. And so there are exceptions to that rule of it working, but this one I guess does work. I want to take more notes, so we're just you have to write these stuff. Day 2. Look at this. Woo! Yesterday, or 5 minutes ago, so we did learn how to find the area between two curves yesterday. Today, look at this lovely objective today. Today we will continue to work on this skill and look at more complicated examples. Tomorrow, which is not tomorrow because you guys are all leaving me for a field trip, we'll see if you're here, Mason. The next step after this, really the only other thing that we have to learn before we can start reviewing for our AP exam, which I believe is 32 school days away, 33 school days away, I don't know. I'm confused which one it is. But maybe yesterday I was counting for today, I don't know, we'll have to check again. But it's really soon, all right? But we have to decide, use this idea of area to make three-dimensional shapes and talk about finding the volume of these shapes formed by curves, which is kind of a cool thing. So, also a big idea for AP stuff. So, all right, here we go. The directions on all of these is find the area between the regions. I bought us all matching shirts to wear for one of our songs in for Pi Day, but they only had extra large. It was on clearance for $1. I told her that my kid had stomach flu, so you know there's a good chance I'm gonna have stomach flu on Friday. So, or that my other kid's gonna have the stomach flu on Friday. So here's the big thing. Should you do this in terms of x's, or should you do this in terms of y, or does it matter? If you do it in terms of x, you have to get it in terms of y equals, right? Like you get y by itself. If you do it in terms of y, then you get x by itself. So my advice is, which letter is easier to get by itself in this problem, x or y? Because if I try to get y by itself, do you agree I'm going to have to take the square root of both sides? Which means I'm going to get a plus or minus. If you get a plus or minus for your equation, right? Like if we tried to solve this for y, we would end up with what? Positive x squared. Is that right? It would be negative x, so it would be positive plus or minus the square root of x. Is that true? You can't just drop the plus or minus. Like that's the positive square root and the negative square root, which means that's two separate functions that you would have to integrate when you're setting that up. All right, so anytime that you would have to get a square root and do a plus or minus, that's where choosing x is not the best option here. But to get x by itself, in terms of y, you would just get x equals y squared, and this one we would just get, x equals 3 minus 2y squared. Yes? So we could graph these. It does work. Both of these are going to be sideways parabolas. We just have to figure out which one's right and which one's left. But let's take a step back from graphing for a minute and think about what if you didn't want to graph this? Step one, we have to find where these two functions intersect. Can I use algebra to find where these two equations intersect instead of having to graph it? By doing what? Yes, substitution is probably a good idea. If they both equal x, can I just set these equal to each other to say this means y squared has to equal 3 minus 2y squared? And if I solve that, that's going to tell me where those graphs intersect without having to make a graph. So if I add that over, would that be 3y squared equals 3, y squared equals 1, y equals plus or minus 1? So those are my bounds. It intersects at -1 and 1 on the y-axis. Here's the other thing we have to figure out. We have to figure out which way we subtract these. Do we take this one minus this, or do we take y squared minus this? So we could actually kind of like plug in some numbers and see which one turns out to be bigger, I guess. But I think about what the graphs look like. We should know what this looks like, right? It's what we just graphed. It's just starting at the origin, opening to the right. What about this one? What's going to happen with, what does the negative do to your graph? It's going to open the other way. What does adding 3 do to your graph? Yeah, it's going to shift it one way or the other, yes, to the right, to the right. And the -2 is actually going to make it wider. So here's my question. Without actually picking a million points, oh my goodness. We know this is going to go like this. We know this is going to go the other way. Do you agree that it's going to, like, it's going to have to intersect like that at some point without actually having to make the whole thing? Could you pick a point just to make You could pick a point just to make sure, but I just want to show you that you don't have to feel like you have to make a super accurate graph every time if you can just figure out which way to subtract. Some people, I don't really approve of this method, some people just like to go with it and guess, and then if they get a negative, then they switch it around. I'm not a big fan of that route, but it works. So I just want to, the stress seems to be when it's in terms of why, of people knowing how to graph it. Goodness gracious. I think we're supposed to take this one minus this one. You agree with that conclusion? Or not? Based on the way that one is, and the other one's going to open it right minus left. So I think we should take -1 to 1 of 3 minus 2y squared minus y squared. Just throwing this out here, we can continue this, but especially when it's graphed for you. Some of the ones in the book were like this. If I'm going from -1 to 1, do you agree that the area under here is going to be equal to the area up there for those two lovely parabolas? Do you agree with that statement? So just throwing it out there that you don't have to do this, but instead of going from -1 to 1, could you just take half of it? Could you do from like 0 to 1 and double that integral? Would that be the same as going from -1 to 1 from that? Why would maybe you want to do that? Is it easier to have a bound of 0 than having a bound of -1? It is. All right, so I'm never going to make you do this. I just want to point out that it's a nice strategy, especially the ones in the book that are pre-graphed for you. If you can look at that graph and see that it's symmetric, that you can just take half of the integral, half of the bounds, and then double it. Does that make sense, what I'm saying there? Do you want me to do the half, or you want me to just do the regular? Okay. So it's the same thing. You're still subtracting 3 minus, I'm actually going to go ahead and say that's 3 minus 3y squared. Let's just put back in line here. And let's see if we get the same answer. We're probably not going to, and then I'll have to go back and do the other. Right. So my 2 is just going to stay up front here, and I'm going to get 3y, and then that's just going to become y cubed. Just 3y cubed over 3 from 0 to 1. So when you're doing this by hand, that's why this is a good strategy, because usually when 0 is your bound, right, you have a y in all of those. So this is just going to be 2 times 3 minus 1 minus 0, or 2 times 2 is 4. Can it be that simple? 4. I got 4 also. Did anybody do it the other way and get 4? You get 4, right? It wasn't impossible to do. It's shorter if you double it. Going to do it the other way? Alright, I'll do it the other way. So I still get 3y minus y cubed, but now I'm doing it from negative 1 to 1. So I get 3 minus 1 minus negative 3 plus 1. So I get 2 minus negative 2. Looks like it's 4. Freaking me out. Alright. Did you bring your calculators today? Okay.
I'm trying to do it the other way and take the absolute value away, but I just took I say I can keep the absolute value. Because on the y cubed and the y squared it's the same answer, but negatively I didn't know if that was just so I'm trying to take the integral the other way and absolute values.
Like in terms of x?
No.
Oh, like just subtracting it the other way?
Y squared minus 3 minus 6.
And then take... Did it work?
I'm not there yet.
Oh, okay.
There's a lot more math.
Yes. We should, from pi 6 to 5 pi 6, maybe be able to make a decent graph of this, but I don't even really care, so how about let's just graph this my calculator. Because there's never going to be a question on the AP exam that makes you graph a trig function like this by hand. They're going to make you evaluate some trig functions without a calculator. If this was sine of x, we definitely could do it super easy, but it's sine of 2x, which means that it's changing the period. The period's now going to be from pi instead of 2 pi.
2 sin x, cosine x.
Or 2 sin x cosine x. I really just want to see what's happening from pi 6 to 5 pi 6. So this is where, if you use a calculator, it's great. You got to understand that window feature. You got to be able to change your window to just look at what's happening between pi 6 and 5 pi 6, or be able to find that on your what's it called? Graph. I'm struggling a lot. Get sick. I'm really tired. It's just rough time. And my other kid doesn't ever sleep. Like, I really think I haven't slept a full night of sleep in over 2 years. Oh, look at this lovely thing from yesterday. 2 sine x. Nope, just kidding. That's not what we're doing. Sine of 2x and cosine of x. Oh my gosh. Have I ever said I hate this calculator? I think I say it every time we do this. We're just going with it. Oh, it says error because of this stupid thing. Alright, we're just going to hit this. So, cosine 2x. I feel like that old person. I know. I feel like that old person, like the new technology, I don't know how to use it. That's how I feel about this guy. I never know, like it annoys me with the Xbox stuff. If I graph this, I didn't even change my window. Oh, look how lovely this is. And then there comes good old cosine. Here's what I would do. They tell me my bounds, right, in this problem. It says, hey, I just want you to find the area between pi 6 and 5 pi 6. Do you realize that if they didn't give us that, we wouldn't know which area we're supposed to find? Because you agree that there's a bunch of little areas in there, like a bunch of closed shapes. They just keep going on forever. So I'm going to change my window from pi 6 to 5 pi 6. And if you really want, you can make your scale go by pi 6. That'd be nice, right? Do we really need our graph to go from negative 10 to 10? We don't. You can make it negative 1 to 1 if you want, but I like going more than that. I'm going to go negative 5 to 5. You got to know how to change your window to make your graph fit what you need. Which one did we graph first again? Sine first? Whoa, oh my goodness.
It's even harder to see on ours. It's like trying to line it up.
It's better to see if you do
Negative 1 to 1?
Yeah.
or negative 2 to 2. That's what I really find.
That looks cooler. Do we have two shapes there? They look very symmetrical, yes? So does that mean you want to just take one of them and double it? Which one should we take? Should we take this one or this one? Or it doesn't matter. But which one is going to have the better bound? What's the best bound to have when you're doing an integral? Oh dang it! There's no zero in this, isn't there? I did this wrong the first time I did it, and I about did it again because I really want this to be 0, but it's not, is it? Because our bounds are pi 6, right? 5 pi 6, which means what's this right here? Pi halves, right? I went by 6, so we could just count pi 6, 2 pi 6, 3 pi 6. Or we could say, when do those equal 0? And it is at pi halves. So I think we should take double from pi 6 to pi halves of sine, the sine minus the cosine. Is that true? The blue one was my sine. Sine was on top. And you might say, well, how come you can do that? Well, notice this is the same shape, but if you chose this one, your bounds are going to be different, and you would go in a different order if you chose this one, but you will get the same answer if you double that, or if you just solve them both separately. All right, so I'm going to do the double one, because why do I want to do 2 when I can just do 1 and double it? So I'm going to go from pi 6 to pi halves, and I'm going to take the sine of 2x minus the cosine of x. And we can do this without a calculator, right? I'm going to go back. I don't like writing on here. I don't care. I'm not going to draw that. We need to put something in there to make that match, right? If you need to write it out as a U substitution, you can. But I'm just going to put the 1/2 out here, because you agree that works it all out if we put a 1/2 and then we take the integral, because the 2x, the derivative of 2x is 2, so you need a 1/2 out there to make a match. Yes? And the integral of sine is negative cosine of 2x. Right? Because if you make the u, then you have to decide if you want to change your bounds, and there's not a u here, so that's why I just kind of did the u substitution in my head. And then the integral of cosine is sine, but it's minus, so that stays a minus sign, right? From pi 6 to pi halves. And yes, on the AP exam, on the no calculator part, it is expected that you could integrate trig functions and that you could plug in some values in a circle. Yes? Oh yeah, thanks. I probably should put a 2 out here. Which means I'm going to do all this and then double it. Alright. So where if this was with, I said show analytically, I would want to see some work here. So I'm going to say negative 1/2. And I'm going to go ahead and put when I take 2 times pi halves, do you agree that that just becomes pi? Minus sine of pi halves minus negative 1/2 cosine of 2 times pi 6 is pi thirds minus sine of pi 6. So then it's up to you on how much work you really show on this. Cosine of pi is negative 1 times negative 1/2 is positive 1/2. Sine of pi halves is 1 minus 1 minus pi thirds is 1/2 square root of 3 over 2, right? So that's 1/2 times negative 1/2, negative 1/4. And sine of pi 6 is also 1/2, right? Minus 1/2. Or distribute that negative, that just changes those both to positive. So that's negative 1/2 plus 1/4 plus 1/2, which is 2 times 1/4, which is 1/2. Did you get 1/2? And then, like, you get 1/4, but then you double it. So that means the area of each little part is 1/4. So together, make 1/2. You don't have to show all that work. You can use your calculator at some point. But I just like to show you can do it without. Just so you know, on my picture, on my paper, I do triangles. But then, here. All right, let's use a calculator for one. It's more exciting to use a calculator. Last one. Good? No? Questions? You just added wrong. It really stinks when you add wrong. It really stinks when you miss a negative. So what I want you to do is grab this on your calculator and see if you can figure out which order we should subtract them in and what your bounds are. So that means you might have to play around with that window a little bit.
I just got to again.
Pi x over 2, right? And then 1 minus x squared. And then, if you make your window really small, it's still kind of hard to see, right? Negative 1 to 1, and then you make it go like 1, and you make this negative 1 to 1. The good thing with mine is I had two different colors, right? That makes mine a little easier to see. So that's my cosine. And then here comes my 1 minus x squared. So mine's different colors, so it's easy to see. I couldn't see on this, so you know what I had to do? I had to go over and I hit zoom in, and then you can make your new center. So like if you couldn't tell which graph was on top, goodness gracious. It's gonna take 12 years to do this. You could zoom in over top of where this goes. All right, that's good enough. We're just gonna go with it. And it'll zoom in just on that part of the graph. It's not even gonna show the graph because I didn't zoom in. Oh look, there we go. You can see that the first one you graphed was the cosine is on bottom and that's on top. Would have been better if I would have actually waited for the cursor to get over there. But that way you can see which one goes on top, right? What's the other thing we have to do? We have to find our bounds, right? I'm going to go back to my window. And just like the last one, do you agree that we have two areas? Like it's going to be over here and it's going to be over here? Just like the last one, is it symmetric areas? So, right, they're both symmetric curves, they're both even. So there's no need to do two of them. Like I'm going to say we're going to double this, and let's just focus on this one. We could just try to look at this and see where it's close to. You can also use that intersect button. I think these both cross at 0. Do you agree with that? That's super great. What about here? Do you know what's out here? Where does 1 minus x squared hit the x-axis? At 1, and cosine also hits, cosine of pi halves x also hits the x-axis there. But we did yesterday, we did that intersect button, so if you're not sure where it intersects, you can check, and you would see that the bounds are actually from 0 to 1. And we want to do 1 minus x squared minus cosine of pi halves x. And again, sometimes you get questions that just ask you to set it up and not to work it out. I worked this out by hand. I think it's probably Monday today, so I don't know if we're going to have enough time to do this. Because you could actually integrate this. This is kind of a U substitution, which means what would we have to put out front to counteract this pi halves that's in there? Over pi, right? Because like the derivative of pi halves x would be pi halves. So you would need a 2 over pi, which means my final answer has a pi in it, which means if you integrate this on your calculator, you're going to get a decimal, like an ugly decimal, if you use Math 9. But I'm okay if you want to use your calculator from here, or if you just want to work it out. I'll tell you my answer if you do want to work it out. I got 4/3 minus 4 pi as my final, 4 over pi, sorry. Or if you just want to type in your calculator and see that you get it too. The setup is really what I wanted to show you of how the calculator can be tricky. Understanding that window function is a really useful thing to do with your calculators. I want you to finish the homework from yesterday, which I think I just took off a couple problems, right? Number 4, number 10, and what was 52? If you didn't look at those yesterday, I want you to add them back on. And then this is day 2. It is on the assignment sheet that I gave you. But try those, all right? Tomorrow, I don't know what time we're leaving tomorrow. Do you know what time we're leaving tomorrow?
We're going to be called down.
I just called students the opposite
Kennedy, Olivia Arnold, Rebecca Perry, Kevin Justice, Jacob Carmichael, Brittany Stevens, Matt Burns, Riley Stone, and Aubrey Williams. To the office, please.
And I did not put the video on from yesterday, if you want it. But I mean, it's the exact same thing we were doing. I mean, exact same thing. We just only did something.
Did you put the video on?
I did.